Put your hand flat on the table in front of you. The desk, the counter, your own knee, whatever's closest. Press down on it. Push hard. Feel how solid it is. Feel the way it shoves back at you, the way it stops your hand cold, the way it absolutely refuses to let you sink through. Good. Hold on to that feeling, because I'm going to spend the next little while taking that feeling apart, piece by piece, until almost nothing of it is left standing. You are not touching that table. The table is very nearly empty. And the thing that's stopping your hand isn't really stuff at all. It's a rule. Stay with me, and I'll show you how the most ordinary thing you do all day, leaning on something solid, hides one of the deepest and strangest facts in all of nature. Let's begin with something nobody on earth will argue about. The table is made of atoms. So is the wood, the metal, the paint, the glass, your skin, the air going in and out of your lungs right now. Everything you can point to is built out of these little pieces, stacked up and stuck together in numbers so enormous that the words for them stop meaning anything. Fine. Now, when most people hear the word atom, a picture pops into their head. A tiny solid speck, a miniature marble, a grain of something far too small to see, but still a thing, with a surface, with an edge, a little hard pebble of matter just sitting there, being small. I want you to take that picture, crumple it up, and toss it over your shoulder. Because if you could shrink yourself down and walk around inside a single atom, the very first thing that would knock the wind out of you is how shockingly, ridiculously empty the place is. Here's the floor plan of an atom. Right in the center sits the nucleus. That's the heavy part. That's where nearly all the weight is bundled up. And then, somewhere out around it, are the electrons. The sizes are everything here, so let me make them real for you. Imagine I grab one single atom and I blow it up, bigger and bigger, until it's the size of a great cathedral. One of the old ones, with the ceiling so high up your neck hurts to look, and your footsteps echo for a week. The whole atom, swollen up that big. Now, where is the nucleus, the heavy heart of the thing? It's a single fly, one fly, buzzing around somewhere up near the ceiling. That's it. In a whole cathedral, the part with nearly all the mass is one fly. And the electrons, the rest of the atom? A few specks of dust drifting near the distant walls. And everything in between, the entire soaring volume of that cathedral, all the air, all the space from the floor to the rafters, is empty. Nothing in it whatsoever. So when I say the table is solid, sit with what that actually means. I'm telling you that a cathedral with one fly in it is solid. And you, your hand, your bones, your beating heart, you are made of these. You are a vast, quiet crowd of cathedrals, each with its single lonely fly, and you are pressing that crowd of cathedrals down against a table that is also a crowd of cathedrals, each with its own lonely fly. Two enormous clouds of almost perfect emptiness, leaning on one another. The atom is more than 99.9% empty, and then you keep adding nines for a good long while. Here's a way to feel it. If you could somehow squeeze all the genuinely solid stuff out of a human being, all the nuclei, pack them together with no empty space at all, the entire human race, every single person alive, would fit into a volume smaller than a sugar cube. The rest of us, all that height and shape and presence, is empty room. That ought to bother you. It bothers me, and I've known it for years, because it raises a question that won't leave you alone once you've thought it. If the table is mostly empty, and your hand is mostly empty, why in the world don't they just pass straight through each other? Two things that are almost entirely nothing ought to slip past one another without the slightest trouble. Your hand should swing through the desk the way it swings through smoke, the way a thrown stone sails through fog. You should be able to wave your fingers around inside the wood and feel nothing at all. Mostly empty meeting mostly empty, you'd expect a whole lot of nothing to happen. But that is not what happens. You press, and something stops you. Something firm, something immovable, something that pushes back exactly as hard as you push. So what is it? What is doing the pushing in all that emptiness? The easy answer is to say, well, sure, the atom's mostly empty, but the bits that aren't empty, the electrons, the nuclei, those are little solid things, and those are what bang into each other. That's the answer most people would give. And it's wrong. The electrons in your hand never collide with the electrons in the table. They never touch. Nothing touches. Let me say that plainly, because the first time you hear it, it sounds like a trick. When you lay your hand on the table, the atoms in your hand and the atoms in the table never ever make contact. There is always a gap between them, a tiny one, but a real and absolute one. That solid stop you feel, that hard wall, all of it is happening across a little stretch of empty space, with nothing actually meeting anything. What's really going on is a matter of charge. Electrons carry negative electric charge, and one of the oldest rules in the book is that two like charges push each other apart. Bring two negatives close, they shove. Bring them closer, they shove harder. Closer still, and the shove climbs steeper and steeper, faster than you'd ever guess. So picture your hand coming down toward the table. The electrons living in the surface of your skin start to approach the electrons living in the surface of the wood, and long, long before they could ever meet, while there's still a gap that is gigantic compared to the size of the electrons themselves, the shoving has already become tremendous. It piles up into a wall, not a wall made of any material, a wall made of force. That's what your fingers are pressing on. That's the firmness you feel. So I'll say it again, and I want it to really land. You have never touched the table, not once in your life. You have felt the table's electrons pushing back against your electrons across empty space, and the nerves in your skin sent a signal up to your brain, and your brain, doing its best, decided to call that signal solid. Every chair you've ever sat in, you were floating a hair above. Every hand you've ever shaken, every time you've leaned your head on someone's shoulder, every time you've picked up a child or held onto someone you love, that was force fields meeting force fields, with a sliver of empty space between you the whole time, keeping you politely, permanently apart. You spend your entire life almost touching the world, and never quite getting there. You might feel like that wraps it up. Electric repulsion, mystery solved, that's why the table is hard. But it isn't the whole story, and the rest of it is stranger than anything I've told you so far. Because there's a second thing holding your hand up, and it has nothing to do with electric charge at all. It's a rule that electrons obey, a flat, stubborn refusal woven into the deepest fabric of how matter works. The rule goes like this. No two electrons are ever allowed to be in exactly the same state, in the same place, doing exactly the same thing at the same time. They simply will not do it. Try to force them into the same situation and they resist, and not because of the electric shoving, though that's still there too. They resist because they refuse, point blank, to share a single arrangement. It's as though every electron demands its own private seat in the theater, and no electron will ever, under any circumstance, sit in another one's lap. The house can be packed to the rafters. Doesn't matter. Each one gets its own seat, or there's a fight. This refusal has a fancy name, and I'm going to ask you to forget the name, because the name explains nothing, and the behavior explains everything. What matters is what the refusal does. It manufactures a kind of pressure out of nothing but sheer obstinacy. Push a swarm of electrons closer and closer together, and they push back harder and harder, not from the electric force, but purely from this insistence on staying out of each other's seats. It is a pressure made of stubbornness, a hardness built from a quantum bad temper, and that bad temper is a giant part of the reason anything at all is solid. The floor holds you up in no small part, because the electrons in the floor flatly refuse to let the electrons in your shoes move into spots that are already taken. The world is rigid because, at the smallest scale, it will not share. And this is where my heart starts to race a little, because the very same rule, the very same refusal happening in the table right under your fingers is also what holds up a dead star. Follow me here. When a star like our own sun finally burns through its fuel, the fire at its core goes out, and gravity, which has been patiently waiting this whole time, begins to crush the star inward. Nothing's pushing back anymore. No heat, no burning, no outward blast of fire, just gravity squeezing a whole sun down toward a single point. So what stops it? What keeps the whole thing from collapsing into nothing? The answer is the electrons. The electrons inside that dying star refuse to be packed any tighter. The same stubbornness, the same flat no. And it is enough, this tiny rule, to halt the collapse of an entire star. You get a thing we call a white dwarf, a sun's worth of material crushed down to a ball about the size of the earth, a single spoonful of it weighing as much as a mountain, and the only thing standing between that star and total ruin is the exact same law that's keeping your coffee cup from sinking through the desk this very moment. Think about that. The hardness you feel under your hand and the last stand of a dying star against its own gravity are the same fact, the same rule, written once at the bottom of nature, showing up in your kitchen and in the graveyards of the sky. When I first understood that, I had to sit down, because it means the solidity of ordinary things, the boring everyday fact that stuff is hard, is not some small dull detail about furniture. It is one of the great structural laws of the universe, and you are leaning on it right now without a second thought. So far, I've kept calling the electrons little things out near the cathedral walls, specks of dust with a location. I have to come clean. That was a convenient lie, useful for getting started, but a lie, and now I have to take it back. Because the electron is not a tiny ball sitting at a particular place. It does not have a position the way your shoe has a position under the table. Before you go and measure it, the electron isn't really anywhere in particular at all. Let me show you why the old picture had to die. For a long time, people imagined the atom as a miniature solar system, the nucleus in the middle, like the sun, and the electrons swinging around it in neat little orbits, like planets. Tidy, pretty, easy to draw. And it cannot possibly be true. And here's how we know. An electron is a charge. And when you swing a charge around in a circle, it bleeds away energy. It radiates. So an orbiting electron would be pouring out energy every instant, and as it lost energy, it would spiral inward, faster and faster, tighter and tighter, and in a tiny fraction of a heartbeat, it would crash straight into the nucleus, and the whole atom would collapse. By that logic, no atom could survive even a moment. And yet, here you are. Here's the table. Atoms last for billions of years without falling apart. So the neat little solar system picture isn't just slightly off. It's catastrophically, completely impossible. Something else must be going on. Something that keeps the electron from spiraling in. So what is really happening? Think about a sound. Picture a guitar string, plucked, humming in the air. While it's vibrating, ask yourself, where is the string? You can't point to one spot and say there it is, because it's smeared across its whole arc of motion, a blur, everywhere along the wave at once. Now think of the skin of a drum after you strike it, rippling in its own patterns, the whole surface trembling in shapes. The electron in the atom is like that. It is not orbiting anything. It is a standing wave, a vibration, wrapped around the nucleus, a pattern of where it might be found, smeared into a cloud, a hum of pure possibility surrounding that tiny speck of charge. And because it's a wave, it has its own allowed patterns, just like a string can only sing certain notes, and a drum can only ripple in certain shapes. The electron settles into these patterns and stops radiating. That's what saves the atom. It isn't a planet falling toward a sun, it's a note being held. And the different shapes that cloud can take, the different ways the electron can wrap itself around the nucleus, are exactly like the different notes that string can play, the different ways that drumhead can ring. Some of the shapes are simple, round like a ball. Some have two lobes like a pair of balloons tied at the neck. Some are stranger, with rings and petals and shapes that are hard to even describe out loud. They are not paths. Nothing is traveling along them. They are the harmonics of a minuscule instrument, and every atom in existence is, in a real and literal sense, a chord being played. And here's the lovely part. Every different element in the world, every entry in the whole table of elements, hydrogen, carbon, gold, oxygen, every kind of atom there is simply a different tune the electrons are allowed to play around a different size nucleus. The whole of chemistry, every reaction, every material, your body, your breath, the wood of the table, the iron in your blood, all of it is music. It is standing waves humming around tiny knots of charge. We live inside a song and we call it matter. And here's something you can go out and see for yourself. Because the string only plays certain notes, the electron is only allowed certain patterns, certain rungs of energy, and no rungs in between. It can leap from one rung to another, but it can never rest halfway. And when an electron drops from a higher pattern down to a lower one, it has to get rid of the leftover energy somehow, so it spits out a tiny flash of light. And the color of that flash depends exactly on the size of the leap. Every kind of atom makes its own particular set of colors, its own signature, as unique as a voice. The orange glow of a street lamp, the red and green sparks of fireworks, the colors burning in the hearts of distant stars, those are atoms singing their notes out loud. So when you look up at the night sky, you are not only seeing light, you are hearing, with your eyes, which atoms are out there and exactly which songs they are allowed to play. But let's not forget that lonely fly back in the middle of the cathedral. The nucleus. That's where the weight lives, remember. Almost every ounce of the mass of an atom, and so almost every ounce of you, is packed into those impossibly tiny nuclei. So let's shrink down once more and go inside one and ask the simplest, most innocent question we can. What is it made of, and where does all that weight come from? Well, the nucleus is built of protons and neutrons, crammed together tight. And each of those, it turns out, is made of still smaller things, called quarks. 3 of them apiece, give or take, bound up together by a force so powerful and so unlike anything in daily life that physicists, fresh out of poetry that day, simply named it the strong force. And think for a second about how strange it is that the nucleus holds together at all. It's packed with protons, and every proton carries positive charge, and positive charges, as we just said, shove each other apart, hard. And here they are, jammed in unbelievably close, closer than anything has a right to be. By every rule of electricity, the nucleus should blow itself to pieces in an instant. And it doesn't. Something is clamping it shut against that ferocious electric repulsion, something even stronger, working at even closer range. That something is the strong force, and pound for pound it is the most powerful thing in all of nature. So inside that one lonely fly there's a war raging, electric repulsion straining to rip it apart, the strong force holding it shut, and the strong force is winning, just barely, in the smallest and most violent space there is. Now here's a sensible guess. If a proton is 3 quarks stuck together, then the weight of the proton ought to be the weight of those 3 quarks added up, plus maybe a little extra for the glue. That's the reasonable expectation. That's what anybody would assume. And it is spectacularly, almost comically wrong. When you carefully weigh the 3 quarks inside a proton, and then weigh the whole proton, the quarks turn out to account for only about 1% of it. 1%. The other 99%, the overwhelming bulk of the proton, the bulk of the nucleus, the bulk of you, is not made of any stuff at all. It is the energy of the force. It is the wild, churning, furious energy of the glue itself, the violent storm of the strong force whipping around inside the proton, the motion and the fields, all of it locked up and held in place. And energy, as a certain clerk in a patent office worked out one very good year, has weight. That little equation you've heard your whole life, E equals mc squared. The E is energy, the m is mass, the c is the speed of light. And the equation runs both directions. Mass can become energy, yes, but energy is also mass. Trapped energy weighs something. And almost all of your weight is exactly that. Trapped energy. doing a very convincing impression of a thing. So stand on the scale tomorrow morning and read the number, and understand what it's actually telling you. That number, your weight, the solid heaviness of you, is almost entirely not matter. It is energy. It is the bound-up storm inside the trillions upon trillions of protons and neutrons that make you, the locked-away fury of the strong force, dressed up as a person standing in a bathroom rubbing their eyes. You are about 99% not made of things. You are made of the energy of things, holding furiously onto one another. If you could ever unlock all of it at once, the energy bound up in one ordinary human body would be enough to level a city. You walk around all day, mild and unremarkable, carrying a hidden sun inside you, bound up so tightly and so quietly that you have never once felt it. And that empty space, the vast nothing inside the cathedral between the fly and the dust, the emptiness I started this whole thing with, even that turns out not to be truly empty. Go down to the smallest scales, and the vacuum itself will not hold still. Fields fill it, trembling and flickering. Particles bubble up out of pure nothing and vanish again before anyone can catch them, born and gone too fast to ever be pinned down. The emptiness inside the atom is not a calm, dead void. It is a restless quiet, full of motion you can never quite see, like a pond that looks perfectly still from the shore, but, looked at closely enough, is alive and swarming all the way down. Empty, yes, but never for one instant at rest. So let's go back, all the way back to your hand on the table. Press down on it one more time. Feel it push back at you. And now look at what is really there, underneath the feeling. Your hand is a swarm of nearly empty atoms. The table is a swarm of nearly empty atoms. They never touch. What you feel as solid is the electric field of one cloud of charge shoving against another, across a gap that never closes. What you feel as hard is, in good part, a quantum refusal, electrons flatly declining to share their seats, the very same refusal that holds up the corpses of stars. The electrons doing the pushing are not little balls at all, but standing waves, humming patterns of maybe, the held notes of a tiny instrument, and the weight bearing down through your arm, the sheer heaviness of your own hand, is almost all of it energy, the bound-up fury of the strong force, doing an astonishingly convincing impression of solid matter. You have spent your entire life leaning on the world, sitting in chairs, walking across floors, holding the things and the people you care about completely and reasonably certain that you were touching solid, real, dependable stuff. And you never touched a single thing, not once. You felt forces. You felt rules. You felt energy holding its shape against the dark. The solid, reliable, comfortable, ordinary world, the floor under your feet at this very second, is one of the most magnificent illusions there is, sewn together out of emptiness and force and music and pure stubborn refusal. And here's the part that I can never quite get over. It works. It holds. You can raise a family in a house built out of this. The floor will carry your weight every day of your life, this towering structure made almost entirely of nothing, and it will never once let you fall through. Nature pulled off the single most extraordinary trick in the whole show. It took emptiness and force and trapped light, and it made them feel like something you could lean on. And it did it quietly, perfectly, invisibly, inside every single atom you have ever touched. Or rather, inside every atom you have ever very nearly, but never quite, touched. So do something for me. Go put your hand against the nearest solid thing you can find, right now, and press. And then tell me, now that you know what's really underneath your fingers, whether it still feels the same. Tell me what you feel.